Hope my screen is visible, right? Is my screen visible?
Yes, sir.
Yeah, just in between, just also confront me if I'm asking anything. Okay. So today's topic is more of a regression. So it's an important topic and basic of machine learning. So your machine learning typically, starts with this regression kind of algorithm. Basically, it's a basic machine learning algorithm, and it has two parts. One is simple linear regression, and other one is multiple linear regression. And I suppose that I assume that you might have heard of these two terms, regression and maybe logistic regression. There are a couple of algorithms which are look similar. Their name looks similar, but their work is different. For example, simple linear regression and logistic regression is typically different, but behind it, the mathematical, the formulas works typically similar, but they are two different. One is classifier and other one is just a regression predicting a single value. Okay, so this is your one of the unit in which you have to create some kind of a ML pipeline, you can say the machine learning pipeline somehow, and you have to create this algorithm. You have to understand that this simple linear regression. Okay, so how you gonna build this regression model, and I'll try showing you this using R and Python, but the major part of this session will we will use this Python only, but I'm gonna show you how you can use R programming, because it's also one of the tool that is hitting the market. If you are if you want to go in a medical domain or maybe some other startup, they typically use this R, but extensively in corporate the Python is ruling, right? But you must understand the R as well. Okay, so there are a few, the concepts typically, people ask you in interview that what is regression, somehow what is OLS, that is also important. This one, ordinary least square, and there is something called sum of squared error, the squared error R squared. What is VIF? Okay, valence inflation factor, and there is something called multicollinearity tolerance, lineup based fit. So these are the few terms when you learn this regression. So you come across these kind of a terms, and obviously in exams or maybe in interview they ask you these typical questions, because somehow these captures, these KPIs captures different matrices of regression. So when you fit a best fit line through this regression, you come across these terms. So these are very much important. That is why I'm showing you in the start, so that you get to know that what is all these terms all about. Okay, so, and also I will be explaining you this OLS in detail, what is ordinary least square apart from R squared and sum of the squared error, because these three terms are very much important. So basically what is machine learning. So obviously it combines the programming as well as your stats to give computers the ability to learn without explicitly being programmed. So you just give entire data set to the model, to the computer, and you say, you give some kind of algorithms. For example, if you want your data to be trained through this simple linear regression, if you have one dependent and one independent variable, at that time it just learn from the data. That is a pattern, right? We are just explicitly programming it, okay, without explicitly. Okay, so this is how machine learning works. So machine learning is more of a kind of learning, a kind of a pattern, kind of a pattern learned from the data, right? And there is a difference of there is something similar terms you might have heard of, apart from this artificial intelligence, there is something called generative artificial intelligence, generative AI, or maybe because in generative AI, typically, most of the models, obviously the majority of the models or all the models are used is a pre-trained model. So pre-training is, just a minute, someone is calling me. So let me, okay, just a minute. हम्म, अच्छा अच्छा कब आओगे? So okay, so let me again put my screen. Okay. So, as I was telling, this artificial intelligence, it's just a top, you can say the umbrella, and under which there is a machine learning, and under which there is a deep learning, and then you have NLP, maybe computer vision, and then you have a generative AI, right? So, how, if someone asks you how you can distinguish between generative AI and AI, artificial intelligence. So, basically, in machine learning or maybe in the AI part, you typically you have a data set and then you turn then you just try to make it more, I mean, try to train the model, right, based on the data set. But in generative AI you already have some kind of a pre-trained model, and based on that you try to create some kind of models. Maybe you want to generate a new content on top of pre-trained model. You do not build any or train any model from the scratch. You just fine tune the pre-trained model. So that is the difference between generative AI and typical machine learning or maybe artificial intelligence. Okay, so in machine learning you have a data set and then you train and test the model, right? You create your own model from the data, right? So this is how it makes you generative AI and machine learning different from each other, but they are subset of each other. Okay, so just to give you the context before I start this linear regression or maybe the regression. If you see in the left side, okay, so there is something called supervised learning. We have unsupervised, semi-supervised, and reinforcement learning. So we are interested in this regression part, simple linear and multiple linear regression. And there is also something called a polynomial regression. Okay. So this is not part in our syllabus, but we'll try to stick to this linear, simple linear regression and multiple linear regression because it's a linear, but polynomial is somehow it is fitting some kind of a curve. Okay. And there is something called a classification algorithms, and in coming classes we do have this classification, few of the classification algorithms. We'll cover all these classification algorithms. Okay, so we have logistic regression. Somehow it's look like it's a kind of a simple linear regression, but it is not. Their work is the classification. If you see, this one is logistic regression, the work is classification. For example, if you have spam, non-spam, right, some kind of a email, maybe if you have some kind of marketing material, okay, and you just want to segregate it. For example, you run some kind of advertisement and there are a few people, let's say male is clicking that advertisement more, maybe female is less. So you're classifying, right? So you can apply some kind of a logistic regression, that which all behavior you are capturing through this kind of a digital advertisement. Okay, and you can build a model on top of it. Okay, and then you have some kind of a this support vector machine, artificial neural network, and decision tree. So these all are classification algorithms, just remember that. So that can be used for multi classification as well and for binary classification as well. Okay, so the way you develop any model depending on the use case. If you have, let's say, more than two classification case, for example, if you are building some kind of a sentiment analysis, the model, for example, maybe the positive sentiment, negative, and neutral, you are capturing the three sentiments based on the maybe the Twitter feed of some of the social media, right? And then you try to annotate the data and putting the label. You are creating the entire data set in a supervised manner, and then you're applying these kind of algorithms. So now you have a three labels. One is positive, negative, and the third one is a neutral, right? So it's not a binary always. If you have a more than two, you can apply. So in some of the cases for the classification algorithms, you can apply this decision tree because it's a branching. It's kind of a if and else loop, right? And then we have this deep learning. So we have sophisticated algorithms, for example, CNN, and also deep learning. You can say the ANN is also a deep learning, right? So whenever a layer of a neural network comes in, we call it a deep learning because they put some kind of a layer, so where you don't know what's happening in that layer, right? And then you have unsupervised. So unsupervised, the K means something called a dimensionality detection is PCA. You have anomaly detections, okay? Semi-supervised is self-training or something. So semi-supervised, you can also take an example of this small language model, maybe the large language model, some of the pre-trained model. So they are semi-supervised, okay? And then you have a reinforcement learning, Monte Carlo simulations and all that. And few of the, this reinforcement learning, that is also a part of this machine learning, okay? But our main focus of today's class would be in the regression only, okay? So let's quickly jump on to how this classical and machine learning typically works. So these things, so I'm just depicting it so that you don't get confused that how this classical programming works and how machine learning. If you see this machine learning, what you are giving to the model, you are giving data and the answers means you are giving some kind of, for example, if you are providing a data, let's say of a COVID data, and you are saying right, apply logistic regression. So answer is nothing, but you are also providing the logics right here, data and logics. When you provide to the machine learning, right, data and this obviously you can say the kind of algo you want to, then it gives you some kind of a rules, okay? Rules means, for example, y equal to mx plus c in some of the regression case. So you are passing these two to the model, for example, input and output both to the model, right? Then it is called a machine learning. Machine, then it learns, right? And then it gives you some kind of a logics, some kind of a rule as an output, right? So this is how your machine learning works. And how it is a classical programming, you just give the rules and then data, right? Then it gives you answer. So this is how this machine learning and classical programming works. So now classical programming is being replaced by this machine learning only, okay? Because the machine learning gives you a kind of a pattern in the data if you want to see what kind of a patterns your data is following. But this classical programming doesn't gives you that kind of a freedom and flexibility, okay? So these are the same thing, and the machine learning and traditional programming. I'm just building a concept so that you can understand this how simple linear and multiple linear regression works. So let's see when it comes to this regression, okay? So I might have shown you this kind of a slide earlier as well. So when you say a regression, right, so obviously it's a stats methods performed to estimate the level effect of an independent variable on dependent variable. So here y is dependent variable and x is independent variable. For example, sales and revenue, okay? So the number of, let's say, 100 units of any the products, if the sales happen, let's say some XYZ organizations, some company sells 100 units of let's say bulb, and what kind of revenue they generate. So y is the revenue, right? So it is a dependent variable. Revenue is dependent on number of sales, right? So it is depending on each other, right? So if let's say if the number of the sales of bulbs gets decreased, the revenue will also fall in that line, okay? So it will fall linearly, okay? That is why this kind of a relationship, once you build this kind of a relationship, you call it a regression, because it's a same in, the examples. For example, if one is independent and other is dependent variable, so in that case we call it a simple linear regression, because the if the amount of or for example x increases in x direction, maybe the x unit, so y will also go in that unit also, I mean in that linear way, right? So it's not gonna go in a non-linear way, right? But if it is following some kind of a non-linear, then it will fall under polynomial regression, okay? Some kind of a curve you have to fit in, okay? But our major focus would be on this linear regression and multiple linear regression, okay? So in multiple linear regression, you have more than one independent variable. For example, if let's say in the sales, let's say if you are putting some advertisement cost as well, so that is independent variable. Advertisement cost plus number of sales is equal to revenue, right? So that is your one of the independent variable. Once you increase the independent, for example, the price of a 3 bhk depend on the location, depend on the carpet area, depend on the how old property is, depend on where it is located, okay? And depending on different thing, depend on the kind of the marble they have used, the kind of maybe the lift, whether there is a lift or not. So there are many more factors depending on the price of 3 bhk, let's say. So all the things which I have said right now is independent variable, and the cost of the 3 bhk is obviously the price of 3 bhk is a dependent variable. So it will fall under multiple linear regression, because the one dependent variable is being influenced by 3-4 features, 3-4 variables. So that will fall under multiple linear regression, okay? So by looking at the number of features, you can easily decide that this is a multiple linear regression case, okay? If your data is supervised, so in supervised case you will have one the variables which will have a dependent, okay? So it's a more of like a many input to one output, okay? So that is a multiple linear regression. And simple linear regression, we typically have one input and one output, right, in a simple way, right? So just I'm just giving you this example. For example, so there are variables typically we come across. One is independent variable, other one is dependent, and third one is a controlled environment, so controlled variable, okay? So independent is, for example, the liquid used to water each plant, okay? So the independent variable is the water, how much water you are giving to the plant, and the height, okay? The one thing you change the limit to 1 in an experiment, okay? For example, here if you are giving water to this plant, obviously there is some height, right? I mean the height will increase, maybe the decrease, okay? Obviously if you are giving water, obviously the height gonna increase, but at some time it will stuck, right? So it's an independent variable, okay? And dependent is because the obviously the height, if you are giving water, okay, to the plant, so water is independent, but the height is dependent variable. So because the height is depending on the amount of water you are giving to the plant, right? So this is a dependent variable here. The height is a dependent variable, okay? But what is the this controlled environment, okay? For example, the type of plant used, pot size, the amount of liquid, soil, etc. Okay. So controlled is everything you want to remain constant and unchanging. Okay. So maybe the pot size, so that may be the something which you can control. Okay. So this is how your variables looks like. There are different type of variables, but we'll stick to this independent and dependent variable, because in regression you just come across only these two variables, okay? So dependent and independent variable, okay? Maybe if you take the help of this plant, maybe the sunlight is one of the independent variable, water is one of the independent variable, and also if you are using some kind of fertilizer, right? So these are the independent variables, and the size of the plant maybe in each month, if you take the note of it. So the size of plant, the growth, you can capture it. So that is your dependent variable. Okay. So here on a if I like to explain it, the amount of water, if you see the amount of water you are giving to plant, that is independent variable, and the growth rate is dependent variable. Okay. So once you change the amount of water, let's say if you are giving 2 liter of water to plant X, so obviously, and each month you are trying to capture the plant growth. Maybe if you are a variable from 1 to 2 liter in between, if you are putting water, and if you try to see that what is the growth, right, and keeping other things constant, right. So you will see some kind of a linear plot that if you are giving more water, maybe the plant growth is higher, right? And maybe if you are decreasing the plant, the water, possibly the plant growth gonna decline, right? So this is how you can create a relationship between independent and dependent variable. But how how you can apply the same concept maybe in the marketing, maybe in the HR, finance, IT, right? You will have a different data set. Okay. But how you can formulate this kind of a huge case, for example, if something related with HR, HR domain. So maybe you can check the employability factor depending on the different, the employee is different. Maybe the level of satisfaction you can capture it through dependent and independent variable. Maybe in a finance you try to see how a stock market works. I mean, the what are the factors which influences the the this price of this stock market. So you can relate with this. The concept is the same, but in different domain you can apply this dependent and independent variable concept. So maybe the simple linear regression or multiple linear regression you can apply. So there is something called econometrics. You might have studied this, this subject called econometrics. So majority of the their fundas or ideas based on the regression only. Okay. So now there is something called a cause and effect. So I'm just extending this regression case and just try to build some of the concept on top of it. So there is something called cause and effect. Okay. So maybe independent variable, you can say there is something called a cause, right? So, and what is the effect? Effect is a dependent variable. So let's say I'm putting water to a plant every day. I'm just, let's say I'm giving 1 liter of water in a pot to a plant X. And the effect would be the growth of the plant, right? So there is a causal effect somehow. So how are you going to capture it? Because there is something called a coefficient. So once I saw Python programming through one of the use case, we have a two use case. So in that use case, you can see that a regression gives you some kind of a coefficients. So how one is causing the effect can be captured through this coefficient. So each and every independent variable will have some kind of a coefficient associated with it. So once you provide data to the model itself will give you some kind of weights. So it's a kind of an internal learning, you can say. These are something called a parameter. Okay. So there are two concepts. One is parameter and other one is a hyperparameter. Okay, you might come across these kind of terms. So parameter is nothing. For example, if I have to capture the this revenue, let's say I have a three independent variable. So x1, x2, and x3, and y is revenue. Let's say. So once I have a data set and if I give it to the model, so model gonna give us some kind of a coefficient to x1, x2, and x3. So these all the coefficients which we are getting, it is a parameter. Okay. So it's nothing but the model is giving us something, right? Some kind of a weights with each independent variable. Okay. So okay. So just a minute. Hello. Hmm. भेज रहा हूँ, भेज रहा हूँ. So, uh, let me share you. Just a minute. So, this independent, dependent, and the coefficients and all that. Okay. So these are the few terms which are typically used, but I'll show you what are this, this coefficient and all. Okay. So now, simple linear regression is more of a, this independent and dependent variable. For example, so let's say x is independent and y is a dependent variable. Okay. So you all know that, for example, for a revenue, y is a revenue, x is number of sales. And let's say if you have 100 data points and you just plotted it out, that I mean how your model looks like, because it's a two-dimensional, so you can easily see that how your data points are. And if you are drawing this line, this is just nothing but a straight line somehow. Okay. So this is nothing but once you give a data to the model will give you this line of best fit. Okay. Because it's very difficult for us to plot the, the line of best fit. If you have, let's say, 10-12 data points, you can put a straight line somewhere. But if the number of the data points increases, in that case it's very difficult to plot it out, because you don't know how to plot. Because if let's say it's just a two-dimensional, but for example, if it is a three-dimensional, maybe the four-dimensional, if you have a independent variable, in that case it's very difficult to capture the whole, there's this kind of a line of best fit. You don't know how to put and where to put this line of best fit. Okay. So this is a simple linear regression, it looks like, and this is line of best fit, this red one, and these all are the data points. Okay. So you have just plotted, for example, x is, let's say, 13.7, y is 40, let's say, something like that. Okay. Your data is somehow supervised. So what this relationship or simple linear regression gives you, how strong the relationship is between two variables. If line of best fit passes is through the each, and if it is touching each and every data point, let's say, if it is touching each and every data points, let's say, then this is called the line of best fit. But if you see, there are points which are totally away. Let's say if x number of unit sales is 100, the revenue is, let's say, 200. So you are plotting this point here, but our line of best fit is going here. So it's like a threshold, value of threshold is higher. So this is nothing. The points which are away, somehow they have some kind of a residual or error. Okay. So the ordinary least square try to minimize the this error. Okay. So that is why this regression do have some kind of error coefficients also in the error. Okay. And a regression is something which just typically captures the how two variables are, how strong these two variables are. Okay. The value of dependent variable at certain value, uh, for example, the value of, if you see this one, the dependent variable at a certain value of independent variable, for example, the amount of soil erosion at a certain level of rainfall. Okay. So if let's say rainfall is higher, let's say in some hilly areas, you'll see the amount of erosion of soil is much more, right? You'll not see in the area where the land is very plain land. Okay. But if it's let's say mountain area, okay, in that, if there is some rain happens, there is something called a landslide. Okay. So these are a case of a regression. If you capture it, that let's say amount of water, or maybe the how much rain happens, and what is the association or maybe the correlation between the landslide, you can easily plot it out, a simple linear regression kind of a curve you can fit in. Okay. So these are the few cases you can also use it, and you can understand that how a regression typically works. Okay. So now this one, this is just mathematical equations. I mean, how mathematical equations you typically capture if you have a simple linear regression. So here you have a something called a dependent variable here. Okay, dependent variable. So let's say number of sales. The revenue here. So this is a dependent variable, and x is obviously the number of sales happens. Okay, so once you fit in the entire data set and give it to the computers, and you say just apply this simple linear regression. So what your the model gonna give you is y equal to, it will give you some kind of an intercept and the coefficient of x. Okay, this is nothing but a parameter typically in regression. So it gives you a parameter beta 1, and there is something called a constant beta naught. Sometimes it is called an error also, error term. Okay, so your regression equation somehow looks like a equation of a straight line. It's a nothing but y equal to m and x plus c. This is the intercept on y axis. So when if anyone asks you the equation of simple linear regression, you just remember that equation of a straight line at least, because somehow it is giving a line of best fit is nothing but equation of a straight line, putting a x and y, right, giving using the data x and y. Okay, so it is more of a regression equation giving a straight line, right, line of a best fit. So it's a equation of a straight line only. Okay, so in previous classes I just explained this curve, and today I'm just explaining you again. So how this simple linear regression, the equation looks like. Okay, so if you see this one, there is something, just let me go with this is x-axis and this one is a y. Okay, so this one is nothing but intercept here. Okay, intercept. So b naught mx plus c, and there is error term. So b naught is your intercept. Okay, and x1 is obviously, let's say here is the sales, number of sales, and b1 is your coefficient of x1. Okay, and e is the error term. So the point is these all are observed data points, but if you see, this is a regression line, and sometimes it is called line of best fit, this red one. Okay, and how far your these data points are away from it, these are the observed point. Okay, so how it is away from this line of a best fit is the error term, and then your ordinary least square. Our aim of this ordinary least square is to capture this residual value, or something called how you can minimize this error, so that your model gives you better predictions. Okay, so this is how our regression typically works. Okay, so now just see, this is the same thing, and dependent and independent variable. Okay, so now there are the three things that can happen. So when I'm using the term best fit, okay, at the line of best fit, so what does that mean? So the possibly when I say line of best fit, the line can pass it through the many data points. Okay, there are many data points where line can pass it through. But if you see, if I'm just randomly giving, I'm saying that this is the line of best fit, but if you see these two lines, they are too far away from this line. Okay, this is not practically possible, cannot say it this is line of best fit. If you see this one, each point carries the same weight, and minimize the maximize residual each point. So the possibly this could be your model could give you this line of best fit, this as another way of putting a line, a kind of a uh, you know a, creating a line of best fit. Model can give you this. Okay, there are the three scenarios. But when you give data to the model, how it typically captures, how they come up with the one line of best fit. So they do it through iterations. So they take some data, they scan it once. So this is iteration one. They scan it once, and then they plot something like this, the line of best fit, something like this, and they store it. Again in iteration two, they do this. They scan again the entire data and then plot. the data, and then they sum it up at the end. Okay, and then they give you the line of best fit. So iteration is nothing but a scanning data at each and every time. So iteration 1 means a scanning entire training data once, scanning iteration 2 is second time, third, fourth, fifth. So if you see, when you train any machine learning model, you typically give some kind of iteration, that how many epoch you want. The sophisticated term is epoch. For example, I am saying at epoch 10, just give me the, just train the model. It means my model is gonna scan entire training data set 10 times. So once they scan it for epoch 1, they scan it and they store the result. Again, second time, third, fourth, fifth, and then average it out, and then they gives you the best result. Okay. So just remember that how your model train the, once you give the data, how they come up with this kind of a sophisticated model, right? So the science behind this is the epoch, and at each epoch they scan the entire training data set. Okay. So there is something called residual. The term which I have used is residual. Okay. So in interview they do ask you if they want someone to work as a data scientist or maybe data analyst. They do ask you this residual term, right? It's related with regression. So what is residual? Okay, just understand that this is your line of best fit and one of the data points which are away from it. So this is a residual. Okay, and the below is typically called a negative residual. Okay, so the data points which are away from line of best fit is a residual. Okay, and what typically ordinary list square does is they try to minimize these two terms, the positive residual and negative residual. They try to minimize it, so that, let's say, had it been had this residual on this line of best fit, your model have been one of the ideal case, but typically it doesn't happen, right? You'll get some kind of a residual. There is nothing ideal in life. Same is with the machine learning models. There is nothing ideal, but you do capture some kind of a error terms too. Okay, but ultimate aim of a machine learning model is to minimize the error. How much you can minimize the error, because you are not you will never get some kind of 100% supervised data and error free. So okay, you're gonna get some error, right? But how you gonna create best model out of it, that is obviously the skills of a data scientist or data analyst. Okay, so residual is how far your data points is from the line of best fit is a residual. Okay, and in ordinary least square is to minimize it, how you can minimize it. Okay, so the line of best fit is the result of minimizing the sum of the square of the residuals. Okay, just try to minimize it. Okay, so now if you see this one, also go with the definition that vertical differences between the data points and the possible line of best fit is your residual. Okay, this is vertical. Okay, now how you gonna how you gonna minimize it? The least square methods, which I am using this term frequently now. So now you have this the line of best fit, and this is residual. So observed value is y1, but predicted was this. Your line of best fit is like something which your model has predicted, but once you check in your data set, the value somewhere lies here. Okay, the value is lying here. It means there is some kind of a error, there is some kind of a deviation, right? There is some kind of a residual, right? There is a residue. Okay, so the random error is y bar yi minus y bar, means the your predicted value, what your model has predicted, and the actual value, and you try to minimize it. So you're squaring it. Let's say some negative terms are coming from this, that is why you're just squaring it up and summing it up. Okay, so each and every residual you're gonna square it up and sum it up. Okay, so this will give you method of least square. Okay, least square is something which is very much important, because once you are able to minimize it, your model predictions, their accuracy is gonna go up. Okay, That is why you take help of this least square method. Okay, just because these are the some terms which you must aware of, because I just assume that you know Python programming. You can easily do that. That is not important. But the point is that the how your models are giving the result, you must understand it, because ultimately the when you play with the the real business case, and if your organization requires some kind of a modification, some kind of innovation to the use case, at that time you will stuck somewhere. So that is why you must understand the core concept. That is more important, because where you have to apply this OLS and where not, where you have to take help of multiple linear regression, or where you have to take help of this logistic regression. Because if you know it, the logic, those few concepts, you can easily build the programming and all that. Okay, so now there are few assumptions. Before I show you one of the this Python programming, let me just give you a quick assumptions of this regression. So typically, if you have some regression data set, okay, so in that there are some assumptions, because the models which you are applying has some kind of assumptions. We assume that the every feature in data is normally distributed. Okay, so this point. See this point, every feature in the data is normally distributed. Just let me take one of the example of sales and revenue. So revenue of, let's say, bulb may depend on 3-4 factors. Okay, so those four factors is nothing but feature. Okay, feature 1, feature 2, feature 3. So every feature in the data, your model, when you apply this simple linear regression, it is assumed that each and every feature is normally distributed. So when you plot the data from these features, will have a bell-shaped curve. Okay, so that is a normally distributed. Okay, and this third point is there should be little or no multicollinearity in the data. So this is one of the interesting concept in this regression. When someone says what is multicollinearity, okay, so this questions comes in. For example, the size of a room is one of the variable in your data, and the square feet of or maybe the dimensions of room, there are two features in your data. If you see these two terms are same thing, maybe their measurement is in maybe meter or centimeter or maybe something, but these two data, these two features tells you the same story. So when you plot, these two features will show you more collinearity. They are more collinear, right? So once you apply any regression, or once you try to fit in any machine learning linear regression or multiple linear regression model, you just your work is to check, assume that your data is normally distributed. Second one is check if there are any variables which are multicollinear. If you find it out that there are variables which are multicollinear, you try to remove one. For example, if your builder wants to keep the square feet of a room as one of the variable to keep in your model, then you remove other. Okay, depending on the business case, you cannot remove it. Okay, but just to come across this kind of multicollinearity, you have to remove it, because the kind of predictions at the end you're gonna get it through the unseen data, obviously will hamper if your model captures this multicollinearity. So you have to remove this multicollinearity before building this. Okay, and the mean of residual is 0. It is assumed that the mean of residual is 0. I have shown you what is the residual, and the first one is the independent variable should be linearly related to dependent variable. So these are the some assumptions that dependent variable or independent variable are linearly related. Okay, so these are the few assumptions which you have to take care of before building any linear regression model. Okay, now, so these are the few terms, but how this regression works. So let me show you one of the code. How you gonna code. So is my screen visible? Just confirm it. Sakshi, are you there?
हाँ जी सर.
Okay, so is my screen visible? This is screen, just tell me.
Yes, sir, yes. It's
Okay.
totally visible.
Okay, so what is written here on the screen?
Import pandas.
Okay, this one Untitled 21, na, right?
Yes, yes.
Okay.
Hanji.
Okay, so I'm just showing you how you can create one of the multiple linear regression case. So this one is quite interesting. So just see, there are a few libraries that you have to import. Stats Model API as SM, and there is something called Stats Model Formula API, and there is one of the library NumPy and Pandas. Okay? This one is the basic. Pandas for data manipulation, all that. NumPy, Stats Model AI. So whenever you do some kind of statistical analysis, maybe a regression, maybe you can say elastic regression, maybe time series analysis. So these are the libraries. Just remember few of the libraries, because in an interview, they're gonna ask you that what kind of library you have used, because they do not ask you that just write a program typically. Okay, because if you tell them that I have used this library, they understand that you know the programming, you have done it, right? So just remember that you can say that the stats model is something which I've used while modeling this machine learning, this simple linear regression or multiple linear regression. But if let me run it, okay. So once you run it, it's gonna execute. It will take some time. So this is a Google Colab. So those who doesn't know, you can just open a browser and you can just write it colab.research.google.com. So you will land a page, somewhere which will look like this. Okay. So, and you have something of file, edit, view, insert, runtime tools, and we have editor like this. Then you have something RAM and disk. Okay, and you can also increase the number of the kind of if you want some kind of a TPU or something, you can increase. Okay, so now my data, this data is this is already there in raster data, our data set. So data set is already there. Okay, so let me explain you what is this. Data set is saved in our data set. Okay, so this is historical data. Okay, and what is inside this historical data, let me just click. This is a data frame we are creating, and we have lottery, literacy, wealth, and region is the four variables, you can say, four features to this data. And let me just print head 5. Head, they're gonna give you the top 5 results. If I put 10, it's gonna give us top 10 result. Okay, so this is gonna give us a top 10 result. So I'm just showing you that this data set. Just see, lottery, literacy, wealth, and region. So how you gonna interpret this data set? So someone is, let's say, lottery, their price value is 41, let's say 41 lakhs, someone won it, and their literacy is, let's say, 73%, he's literate, let's say. Okay, and wealth is, let's say, 73 lakhs, he has a wealth maybe, and he is from east region. Okay, this is how you can read this data, right? So now I'm just modeling it. There is something called a model. Okay, so my point is that just to show you that how you can model it, right? So just see, this is user defined. You can write a mod. SMF is coming from here, SMF, because you are modeling it. So here I'm taking a reference of SMS from that library. And there is something called OLS, that is ordinary least square. What was that? That was to capture this residue and all that, so that you can create a linear regression or multiple linear regression. So here this is a multiple linear regression case. So if you see this one, this is a lottery, this is dependent variable. So lottery is depending on the literacy rate, maybe the wealth, maybe how much their income is, and where, from which region that guy is. Okay, so the region, wealth, and literacy depend on this lottery. Okay, whether if they have this region from east, he has, let's say, 73 lakhs, and he has 80% literacy, maybe he is getting a lottery of 1 crore, let's say. Okay, So this is a supervised learning. Your data is supervised. This one lottery is dependent variable, and these three are independent variable. Okay, these three are independent variable. Or in layman terms, you can understand that lottery is output, and we have a three input. Okay, to the model. Okay, and once you run it, you'll get some kind of a coefficient to the literacy, wealth, and region. So now if you see this one, once I run this one, I got some kind of result like this, sophisticated result like this. Okay, so just let me go with this result. Okay, if you see this result, let me explain you this. Okay, here you'll get something called a dependent variable. So here it is saying that lottery was your dependent variable. Okay, the model, what model you used was the ordinary least square, and the method is least square that is used, and these are date and time, and what was the number of observation was 85 data points, and the number of residual was 78. It means 78 data points was away from your line of best fit. It's just a residual, and the degree of freedom is 6. It means number of independent variable was there. Okay, degree of freedom, I'll explain you what is the degree of freedom here. But and there are also a few terms called r squared, adjusted r squared, abstract, probability, and is likelihood, AIC, BIC. These are the few terms I'll explain you. For a time being, just see this one. There is something called a coefficient here. It means just assume it as a linear regression case y equal to mx plus c. But here the case is multiple linear regression, so we'll have something called y equal to mx1 plus mx2 plus mx3, okay, plus some error terms plus some coefficients or some intercept. So here if you see, the model is giving us intercept of 38.6517. It means it is cutting on y-axis, that is the intercept. And the region wise, east, north, south, west, these are 1, 2, 3, 4 terms, fifth and sixth term. Okay, there are 6 terms. It means the degree of freedom, df, is 6. It means there are 6 independent variables. So in which, if you see this one, the region is also categorized. Okay, so that it gives you 4 more these variables, and 2 was literacy and wealth. Okay, now so okay, so now, and each and every independent variable has some kind of a coefficient. If you see, the region east has minus 15 point something as a coefficient, north is minus 10, south is minus 4, region is, let's say west is minus 10, literacy is minus 0.185, and wealth is 0.45, this one. So these are the sum coefficient and some error term also. So while once you run this model, your model had also captured this error. So error terms is coming from this residual, right? Y minus y bar, they are square. Okay, so if you see this standard error, all are in positive. Okay, it's not negative because it is squared already. Okay, then t, probability of t is there. This is some the value, the significance level at 0.05 percentage, and at 5% and 10% of this probability, this p value, whether this is significant or not, that can be captured through it. And below you'll see there are a few terms which are very much important. Okay, so this is omnibus 3.04. What is this? Probability, skewness, kurtosis. Okay, these are the 2 terms. That is called Durbin-Watson test. These are some few
Sir,
tests.
your screen is not visible, sir.
My screen is not visible now.
No, sir.
It was 1 minute. Okay, just tell me if it is visible or not, because 1 minute, 1 minute. Now it is visible, just confirm. Is it? Is it visible? Is my screen visible? Sakshi, is my screen visible? I think, I don't know.
हाँ जी सर.
Screen visible है?
Yes, sir, it's visible.
Okay, someone said it's not visible. Okay. So these are the few terms which are which is to be explained. Okay. So let's say uh, you know uh, the terms before I go to the next step. Let me show you the explanations of it. Okay. So if you see this one, the explanations and all. So our output looks like this here. So output is obviously the dependent variable is lottery, R squared, adjusted R squared, and all these things are there. Okay. So maybe in exams, you might be asked to explain, I may give you this output, kind of output, and I may ask you that how to explain it. Okay. So now, if you see, this is the output which I have got. Now, how you gonna explain it? So the dependent variable, you're gonna write this is a dependent variable. Lottery was a dependent variable. And the method used was ordinary least square. What typically OLS does is to estimate the relationship between the variable. And the method used was the least square. What typically used this least square is minimize the sum of square residuals. And the number of observation means data point was 85 that is used, the data points. And the degree of freedom is 6, it means the number of independent variable is the degree of freedom. And the residual is 78, it means the number of points which are passing, the passing away from your line of best fit is a residual. Okay, how far your data points is away from the line of best fit. Then if you see the R square is 0.388, let me go down, and if you see the R square is 0.338, what does that mean? Okay, so residual is this R squared value, because whenever you have a different machine learning models, let's say if you are training 2-3 machine learning models, and you like to see that the performance of that model, so in that case R squared typically helps you. Okay, so here we are using this multiple linear regression. So multiple linear regression captures this R squared as well. Okay, so it means 33.8% of variation in the dependent variable is being explained by the model. Okay, this simply means 38%. It means lottery is being explained by 33.8%. Okay, and if there are 33 times, out of 100, 33 times people can win if they have maybe the educations, or maybe these all variables were there. Okay, the wealth and literacy and the reason. Okay, so, and what is adjusted R square? Adjusted R square is the number of predictors. Okay, so here we have a 6 predictors, suggesting a slight decrease in explanatory power. Okay, for example, if you are let's say if you have a 10 independent variable, and if you are adding 5 more independent variable, maybe your the explanations of your model may decline. So that is why when you select independent variable to model this machine learning model, or maybe multiple linear regression, you have to take care of the number of variables which you are using to train the model. Because if you are using more than 10-12 variables, at that time the model's explainability will fall drastically. So that is why R square captures it, the explanatory power of independent variable. Okay, and what is f stat? If f stat is giving, let's say, 6.36, so at least one independent variable is statistically significant. So this one tells you. Okay, okay, and then probability of f stat, if it is very small, indicates that the overall model is statistically significant. It means majority of the data points which are coming from your bell-shaped curve. Okay, the middle of the bell-shaped curve. Okay, this is how it typically you can interpret it when it comes to significance. It is not falling under the rejection reason. Okay, so and then we have something called coefficient and statistical significance. So coefficient is nothing but the independent variables, something they captured it once your model is trained. So let me go down. If you see this one, intercept is this one. This is nothing but the variable at the reference. This is just an intercept. So the lottery value when all variables are at their reference level. And also you can say the value which are cutting on the y-axis. Y is nothing but your this lottery. Okay. Region variables, differences in the lottery spending relative to the omitted reference region. The region, the region variables, that is north, east. These are the differences in the lottery spending. Okay, how much they are spending. Okay, the region, let's say the north region is spending, let's say 30 crore, west is 40 or something. Okay, literacy is one of the variable, no significant impact on lottery spending. So this variable has a no effect, literacy, so you can omit it. Okay, here. Okay, because your model doesn't if you remove this one, there is a no effect of it. Wealth is 45, so significant positive effect, higher wealth is associated with increased lottery spending. So I mean, the people do, those who have higher wealth, let's say 45, let's say this assume 45 crore. Okay, so obviously if they have 45 crore, they can spend 10 12 lakhs. Okay, so now what your model is giving, the clue is that if you remove this literacy doesn't play any role in lottery spending. Okay, so you can easily remove that. Okay, so this is how you can interpret your model output, because it's not about how you come up with, how you can create a model through Python, but how you interpret is also important. Okay, one of the also point of this model is the diagnostic stats. So there are the few terms which we come across is, let's say Darwin Watson. These are just few tests. Okay, so what Darwin Watson test measures is autocorrelation in residual. A value close to 2 says that no serious autocorrelation. It means there is no any variables, they have some autocorrelation. For example, the size of a room and the square feet of a room. These are the two variables. They are autocorrelated. They are correlated. That means autocorrelated. So here, once you run it, if Darwin Watson test gives you a value closer to 2, it means there is a no serious autocorrelations. Okay, so if you see Darwin test is 1.7, it's closer to 2. It means there is no any variables with so autocorrelation. Okay, this is also one way out to remove outlier, or maybe you can for a feature engineering, if you want to remove it, just go and check the Darwin Watson test. If it is closer to 2, you will see there is a no autocorrelation. If it is less than 1 or may probably closer to 1, then obviously there is your model has serious problem that you haven't omitted any autocorrelated variable. Okay, 371 test multicollinearity. A condition above 30 indicates potential issue, but 371 says that the serial multicollinearity might be present. So in this case, there might be a case of multicollinearity. Okay, a case of, for example, in these regions possibly. Okay, so and if you have to summarize it, because ultimately your organization is asking you to summarize this, the model's output, how you're going to summarize it. Okay, so obviously the model 33.8% of variance in the lottery spending your model is explaining, which is quite good, but maybe how you can increase it. Maybe your organization is asking you to increase the explainability of the model, the explainability of the lottery spending. So how you gonna explain it, I mean how you gonna improve the model performance. So obviously you'll take more data, you will try to remove few of the features, and then you again retrain the model, right? So as model is explaining, only 33.8% variation in the dependent variable, I mean the variation in the lottery spending. Okay, which is quite good, but if you increase the sample size, maybe you can hit maybe 40%, 50%. Okay, model at least explain 50 to 60%, then only model somehow captures the the variability in the dependent variable. Okay, the wealth is the only significant predictor because education was not. Only the wealth was explaining well. Okay, meaning wealthier individuals spend more on lottery. So this is how you can create a correlation. So as in correlation class I was telling that the base of this correlation, you can use it in regression also, because here one of the variable wealth is giving you a clue that someone who is wealthy gonna spend more money in lottery, right? So this is establishing the fact, right? So factual establishment can be done through this regression also. Okay, the regional difference in literacy do not have a significant effect. Okay, it means the regional differences, if someone is from east and west, north and south, doesn't play an important role. That if someone is from south, it doesn't mean that he gonna spend more money in lottery, right? It's not. So it is also somehow establishing a fact, or okay, the kind of a correlation. Okay, and potential multicollinearity exists as indicated by the conditional. Possibly you have to check the multicollinearity in this region wise. Okay, but the region and literacy doesn't play any important role in lottery spending. Okay, it's only the wealth. So now how you gonna give suggestions to your manager that okay, so which variable is to take while building this model, right? So now your model is giving, you're gonna show this output or OLS to your manager that okay sir, the lottery is being, the number of spending on lottery is directly associated with the wealth only, so why not to keep wealth, right? So this is your logical explanations driven by the data, right? Driven by the fact, right? So this is how your machine learning works and how you take a decisions, how you can set up the decision. This is how typically it works. Maybe your area might be different, maybe use case might be different, maybe maybe you may come from a different functions, but the basic idea is whenever you take any decisions, it should be data driven, right? It should be a logic. You must have something, if you have some numbers to play with. So here now I can show you, I showed you that how through this regression output you can take a decisions that and which variable is to keep and which variable is not to, right? So this also can help you in a decision making. Okay, so this is very much important. I may ask you this kind of a questions in exam to explain the output of regression model possibly, and you have to explain like this so that you understand the entire concept behind that. Okay, so now let me come quickly back to my slide. Hope my slide is visible. So mathematically, you know that I have shown you, this was the small case which I have taken last time, that the salary is dependent variable and the number of experience. Possibly you could be you might have 13 years of experience and you might be getting 64 lakhs LP, right? Possibly there might be a people who do have 3 or 5 years of experience, they might be getting 30-40 lakhs. Okay, so whether if you plot and you have to, there are a company who just want to predict the the salary of a data scientist. Okay, so they do have historical data and they do capture their educational background, if they are from a organizations, or maybe from a tier 1 or tier 2 educational institute, or maybe from they have done maybe from any other the previous record is from any other good company, or maybe they have experience that they do have some kind of a certifications. So that could be one of the factors while giving this package, this compensations, whether they're gonna get 20 lakhs, 25 lakhs, possibly 50-40 lakhs. Okay, so there are different industry, the entire recruitment industry or maybe HR domain in any company works like that. They do have some kind of a numbers associated with it. They put some numbers and then they give you some kind of a compensation. So also there are a few organizations who create some kind of models, AI models, and they give entire fill in the data and they try to predict your salary, what could be your potential salary, right, based on the different factors they capture it. Okay, so that this one, so I'm just skipping it because this is just a math that how regression, OLS, how it comes, because I've just shown you through Python programming. But how mathematically you can calculate, this is how it works. Okay. So now let me show you, this one is the R. You can run it. It's just a small program. So I'm not explaining it here. Just a small. This is similar to the Python. Okay. So let me just explain you this one. This one is year of experience in Python, in R. This is 2, 3, 5. These are the experience. And the salary, how much you gonna get, right? 15, 28, 42, 60. These are the lakhs. In step 2, we are just fitting the model. That this one is linear model, LM, less than minus. This is how we write it. And salary is dependent variable, and independent variable is year of experience, and then you write summary LM. So this will give you some kind of a stat, right? Minimum, interquartile value, median, third quartile, maximum value, and this give you some kind of a coefficient, right? Similar to Python, right? So year of experience, the intercept typically you got is, let's say, 4.76 or something like that. Okay, intercept is 9.1890. So you get some kind of equations similar to this Python, right? So here, once you have this R programming, so salary is 9.189. This is the C part, and the year of experience is independent variable, and their coefficient was 4.7916. So whenever a new, someone having 15 years of experience, you are just putting in this formula, just multiply by 15. So what salary he gonna get it if he has a 15 years of experience? So once you put in the formula, it is approximately $81 maybe, okay, per month possible. So this is one way you can formulate this regression. Okay, this is a simple one. Okay, so the R squared value, and R squared value, I have already explained you that how you can use this R squared value, and what is their significance. So just let me go through it. Okay, so if you see this one, R square of means that the dependent variable cannot be predicted from independent variable. So for example, if R square is 0, okay, let's say R square value is 0, means that dependent variable cannot be predicted from the independent. It means there is no effect of independent variable on dependent variable. There is no effect. For example, in the previous case, the literacy was there was a variable, but the variable doesn't have any kind of association or correlation. So if you only run it through this literacy part, you might have got R square value closer to 0. If R square is 1, okay, if R square is 1, it means dependent variable can be predicted without error from the independent variable. It means ideal case. For example, if it is wealth, in the previous example, and wealth is directly you can say correlated with the number of maybe the lottery, the purchase of a lottery, let's say. So if you have some the data capture, you might got R square value, might have got R square value closer to 1, right? It means your lottery, the buying lottery might have predicted well with your the wealth, how much wealth one carries, right? So R square of 0.991 means 99.1% of the variance in Y is predictable from X. How much variance in the data, the dependent, for example, in the lottery, the buying of a lottery, spending on a lottery, if our model is giving 90.1% of R square value, it means your wealth is being explained 99.1%. The lottery spending is explained 99.1% from the wealth. That is the independent variable. So the adjusted R tells you that the percentage of variation explained by the independent variable, and we have some adjusted R square. Adjusted R square will penalize you for adding independent variable. So why we are using there is also a few questions related with R squared and the adjusted R square. Okay, Adjusted R square, if a model is giving you adjusted S square, it means how you can pick the independent variable. I mean, whether, let's say, your model has a 10 independent variable and you have trained that model on those 10 independent variable. So these 10 independent variable, then obviously it give you some kind of adjusted R square. So adjusted R square means, I mean, if you are adding more variable to predict, the model, so in that case, it will give you some kind of a penalizations. Okay, it will penalize the model. It means that you cannot increase the more variables. Possibly, if you decrease few variables, model gonna give you a better result. Okay, so R squared value will penalize it if you increase the number of independent variables. So adjusted R square value 0.99. What does that mean? If adjusted R square value is coming closer to 91%, the model is very well suited and does not contain any attribute which is not helping to predict Y. It means one of the clue, right? This gives you a clue that if R squared value, adjusted R squared value is much higher, right? It means your model is explained well. Your dependent variable is being explained by the independent variable in very well manner. Okay, if R squared and adjusted R squared value are closer to each other, then that means selected features are relevant and doing great, right? If they are poles apart, then it is clear indication that the features selected are not relevant. So people may ask you that how R square and R adjusted R square play important role in feature selections. Okay, so if your R square and adjusted R square is coming closer to somehow 1, it's not practically possible, but just assume it that it is coming closer to 1. It means the variables which you have selected for a predictions, the independent variable which you have selected for a predictions is much better. This means your selection of variables is in a right directions. Okay, so these are the some clue you can derive from R squared and adjusted R squared value. So these are the few terms which are very much important in context with your the interview and all that. Okay, so let me take another example of this stock prediction. So I mean, how your stock predictions, you can model it through this multiple linear regression. So this is also one of the regression case. But here, if you see, you can also model it through the time series analysis. So there is one element of month here. If you see this one, the month. So month is here. So how you gonna associate this with the time series analysis? But here we are just keeping it as a multiple linear regression case. We are just treating it as one of the variables. Okay, not modeling it using time series analysis. You can also forecast this stock price index through time series analysis, but here we are as we are just using this multiple linear regression, so we will stick with it. Okay, for example, in 2017, the month 12, the interest was to 2.75, unemployment rate was 5.3, and the stock price was 1464. Okay, this is your entire data set. Okay, but in 2016, in January month, interest rate was 1.75 percentage and the unemployment rate was much higher. It's 6.1%. Okay, and what was the stock price was 7.19. So how you gonna model it, right? These are the data sets which you have been given, right? So how you gonna predict the stock price? And now let's say you have these features. So if you see this one, somehow this stock index price is your dependent variable, which is depending on, these are the factors. Okay, maybe it is depending on your unemployment, interest rate, may not depend on the year and month, but obviously it is depending on interest rate and unemployment rate. If you see, if there is an unemployment rate of, let's say, where is the hiring unemployment rate, 6.2, let's say 6.2. Okay, so a stock price is 7.4. Okay, so somehow it is fluctuating. Okay, if unemployment rate is less, stock index price is higher, right? So but one glance you can see somehow some few patterns. You can easily see that okay, there is some kind of a correlations. If stock price and unemployment rate somehow negatively correlated, but how you gonna model, because you have also one of the factor, that is interest rate, how you gonna include it in your modeling, right? So for that, obviously you have to find it out which variables, which independent variables you have to take care while modeling this multiple linear regressions. Okay. So obviously we know that stock index price is a dependent variable, and unemployment rate plus interest rate is one of the factors which are which are independent, but stock index price is a dependent variable. Okay. So how are you gonna model it, right? So for that modeling, I have used it through the R programming. Okay. So R, this R programming, if you capture the year, month, interest rate, and all that, unemployment rate, stock index price. So we are just creating a data frame. Okay, it's nothing but a data frame. Previously, if you see, we have a year, month, interest rate, unemployment rate. So we are assuming that these are all are the factors which are, let's say, independent, but depending on a stock price. So now we are just plotting it. For example, just to see the scatter plot means, for example, unemployment rate and stock index price. So a stock index price is a dependent variable, and an unemployment rate is independent variable. So whether, let's say, if you see this one, if unemployment rate is higher, people are less investing in this stock, maybe the stock, right? This is how it's typically captures. So because unemployment rate means people doesn't have money, right, to invest in stock. This is a simple logic. Had people have if people have a high, I mean they are getting a salary, maybe they are employed enough, obviously they're gonna spend money on a stock, right? So this indicates that the higher unemployment, if any country has a higher unemployment, it means stock, the stock market of that country will fluctuate. Okay. Let's say if some the stock, the unemployment rate is 5.4, right? Okay. So if you see the stock index price is much higher, right? So this is a negative correlations. Okay. This is negatively associated and this is negatively correlated. If stock index price is higher, it means people are employed. This is one way to capture, right? So if I like to know the country's, the economic or maybe the literacy rate, I'm not gonna see the literacy rate literally, but I'm gonna see the stock index price. If a stock index price is hitting higher, obviously I'll assume that there is less unemployment rate. Okay, people are employed, people do have a jobs, people are earning it. Okay, so how are you gonna model it? Through the regressions. Okay, I'm just giving you idea that that which all are dependent variables. So stock index price is a dependent variable. This is a tilde sign in R. Typically people give it a tilde sign. This is a relationship. So stock index price is related to interest rates and unemployment, and we are just removing those the year and the month because that variable is not affecting the stock index price. It doesn't mean that if it is December, then the stock index price would be much lower. It doesn't mean that, okay, or maybe higher. So it is just the interest rate and interest rate plus unemployment rate. Okay, these are the two critical factors which are dependent on the stock index price. Okay, so once you apply this, this in R, so we have a data set. So now training on data set, summary model. So this is a fitting the model less than minus LM is linear model. LM, this is LM, this is a linear model, and this one is dependent and this one is independent variable. So once we type in the summary model, this gives us some kind of a summary and the R has one of the beautiful feature of putting this asterisk. Okay, also Python gives you a asterisk. It means interest rate. If you see this one, just let me jump on to the last, the columns. This one, interest rate and unemployment rate. Okay, so if you see there is a asterisk. Okay, this means they are significant. It means interest rate and unemployment rate has effect on stock index price because they are significant. Okay, the value is somehow lying between 0.05. Just see 0.05. It means the value which are interest rate and unemployment rate falls under region of acceptance region. Okay, and in the bell-shaped curve, it is falling under acceptance region. It means unemployment rate plus interest rate has an effect on stock index price. So this is how you can interpret it. If you see the multiple R squared value and adjusted R squared value much higher, closer to 1. So as we know that if R square and multiple R square, adjusted R square value and multiple R square value somehow closer to 1, it means your model is very well, your dependent variable is being explained very well by dependent variable. Okay, I mean these are the two factors. I mean your model dependent variable, that is stock index price, is explained 88% well by the interest rate and unemployment rate. So this is how you can interpret the model. Okay, so these are the few terms. By looking at the stats, by looking at the output, you can easily come up with some kind of analysis that the model is good or not, and which all factors play an important role in predictions, and which all factors has a less dominant factor and which has a higher dominant factors that to be included in your model, right? So this is how your regression typically works. So I mean how you explain it. For example, if you see in a step 4, a multiple linear regression model equations. So our model is giving this this regression model equations. Okay, so here if you see this equations, stock index price was the dependent variable depending on interest rate and unemployment rate. But once you through this output, the previous output, because the output was giving some kind of a coefficient, this is the estimate is nothing but a coefficient. Intercept is 1798, interest rate is 345. You have to multiply interest rate with 345 and unemployment rate by minus 2.50.1. Okay, so now stock index price is intercept is 1798.4 plus x is your interest rate, that is being multiplied by the coefficient 345.5, that is coming from our model, and unemployment rate is negative minus 2250.1. Okay, this is unemployment rate. Okay, so it means if unemployment rate is higher, it means your stock index price is gonna go down. Okay, if unemployment rate is higher, if unemployment rate is lower, your stock index price is gonna up. Okay, so how you gonna explain it? Okay, so if you increase, let's say 1 unit of interest rate, a stock price will increase by 345. So here if someone asks you to interpret it, so for example you will say if I increase 1 unit of interest rate, my stock index price will go up by this coefficient 345.5. Or if I increase by 1 unit of unemployment rate, my stock index price will decrease by 25.1. It means even a slight increase in unemployment rate, just see how much it is creating a problem with the stock index price. Your stock index is gonna go much lower even at 1 unit of unemployment rate. It means that is why a few countries try to keep unemployment rate at certain level. Okay, they do not let unemployment rate go higher. Okay, that is why different organizations or different companies, or maybe different government try to keep inflation and unemployment rate at certain level so that they can calibrate it. Okay, you cannot increase much unemployment rate because this will hit hard on your this stock index price, because if your stock is performing well, obviously the investor is gonna come to your country. Okay, they only see this stock index price, otherwise they will not invest in. Okay, so these are the some factors which play important role, and you have to look these models also through the third eye or the bird view. Okay, so this is how you can create a model, but how you can create a predictions now. Okay, now your model is trained, now you know the explanations of the model, everything you know. So how you gonna let's say unemployment rate is given, let's say interest rate is given of 1.5. Let's say someone has given you that interest rate is 1.5 and unemployment rate is 5.1. So what will be the the stock index price? So you just simply put in all the values and you will get a stock index price of 866.0. Now you have a formula, now you have equations, so now you can play with. For example, the government has this data now, so what they gonna do? They will try to decrease the unemployment and they will try to increase the interest rate, right? Interest rate, if you are increasing the interest rate higher and decreasing the unemployment rate, they will have somehow an index price of, let's say, more than 1000. Okay, that is what typically government wants to, because one of the factor is in negative and other factor is in positive. Okay, this is how typically this predictions works when it comes to this the stock indexing and all that. So now you are able to create a model, now you are able to take a decisions, now you are able to interpret it, right? So this is all you can do with. And also you can if you have another data set of different domain, you can also apply this kind of model and you try to understand it, that how different factors play an important role, whether positively or negatively. So regression is something which gives you a clue of correlation, causations, multicollinearity, variance inflection factors, R square, adjusted R square, how you can decide, how you can take a decisions and all. So this is one of the basic algorithms which have so many things embedded in it. Okay. So what is multicollinearity? Okay, so I mean when it comes to multicollinearity, as I already told you, that one of the factors which you have to take care while designing, while selecting this features in multiple linear equations. Okay, so let me just frame this the multicollinearity. So this is kind of a conditions. Okay, so if you see a dependency or association between the independent variable or the predictor variable. Predictor variable is nothing but independent variable. A significant correlation between independent variable is often the first evidence of presence of multicollinearity. If there is some association between the independent variables. For example, I was giving an example of size of the room and square feet of the room. Okay, so if your data set has two features, then you have to think of, because these are the two features which will show higher multicollinearity. So that you have to pay the price of it, because your model their prediction accuracy will be hit hard by this multicollinearity in your data set. Okay, so now how you're gonna remove it, I mean how you're gonna minimize it, and how you come across and how you solve the problem of multicollinearity. Okay, so just take this example. I mean, imagine you went to watch one of the rock show, and there are two singers. Just pay attention here. So there are two singers, a drummer, a keyboard player, and two guitarists. Okay, so we have two singers, a drummer, a keyboard player, and two guitarists. So just assume it that these are the independent variable, the features in case of a multiple linear regression. So we have a two singers, drummer, a keyboard player, and two guitarists. You can easily differentiate between the voice of a singer, as one is male and other is female. But you seem to have a trouble telling who is playing better guitar. Okay, okay, you don't know. Maybe you are familiar with male and female voice. But when it comes to instrument, because instrument works in a similar way, whether a male play or female play, it doesn't depend on that, right? So it's very difficult for you to distinguish who is playing this guitar, right? Who is playing better guitar, right? Both guitarists are playing on the same tone, same pitch, and at the same speed, right? If you could remove one of them, it wouldn't be a problem, since both are at almost same, right? So let's say if you hired two guitarists and they are playing at the same pitch, same level, or same speed, right? It means they are redundant, right? Even if you remove one, other can play well, right? So this is one of the multicollinearity, means higher collinearity, higher associations. Okay, The benefit of removing one guitarist is cost cutting and fewer members in the team, because if you have, let's say, 10 members and you are paying the price, right? So if you are giving a fee of all 10, if you remove one, you can cut the cost, right? In machine learning terms, it's a fewer features for training, which leads to a less complex model. Okay, so maybe if your model is handling 20 features, so obviously the complexity, the computational cost, the resource, and everything, you have to pay more, right? Your model will take more time, more computer, more computing space, computing time, okay, everything, even in terms of money, right? If you are training this model on maybe the Google Cloud, obviously it will cost more, right? So just to come go away with this the complexity, you have to take care of this multicollinearity. So here both guitarists are collinear, right? Because they are playing with the same pitch and same speed. If one plays the guitar slowly, then other guitarists also play the slowly, right? So multi my aim is here to make you aware that what is multicollinearity. It means it is the same thing and the size of the room and the square feet of the room, right? So two same variables telling the same story, right? So here also the two guitarists playing at the same pitch, same speed. I mean, it's a significant. It's just a insignificant, right? Because if you remove one, other can do well, right? So this is a concept behind your multicollinearity in multiple linear regression. Okay, so just to remove that, obviously there are a few, the r square, adjusted r square value. There are many more terms which we have checked out before you do entire final the modeling part, right? So if you see this one, now you have a the data, the big mart or the data set. Okay, so these are the few terms. Now you have data set is given. Okay, let's say item weight, visibility, MRP, outlet established in the year, this, and these are the sales. These are the data points. So my point is that just to show you that if there is some variables which are multicollinear, right? So how you gonna do that? So you will do some kind of this correlation matrix. You will create a correlation matrix. So if you see the item weight and the outlet established here is they are highly correlated here. Okay, item weight and this. So you can remove one, and there is also a way to remove this multicollinearity, and this is called a variance inflation factor. So mathematically you typically try to capture this for the multicollinearity. For this multicollinearity you just try to capture this variance inflation factor, VIF. Okay, so VIF is typically you capture it, or you can create some kind of a this matrix, correlation matrix, and you see that whether value which are 1 means highly correlated. Okay, the value which are closer to 1 is highly correlated. For example, in this case, this displacement and WT is, let's say, weight is higher. They are showing more correlation. So you'll see that whether they have some effect, or if you remove one, whether a model gives you a better result or not. So this is just a mathematical way to come across to solve the problem of multicollinearity, is to check this variance inflation factor. Okay, so a variance inflation factor, this is not part of your syllabus, but just to give you a clue that how you typically captures this. Okay, the typical rule of this multiple linear regression is, if you are capturing this this variance inflation factor, how your factor is, how your feature is inflated. So just keep a value less than 5. Don't go with that. If you have a variance inflation factor more than 10, it means there is some problem. Okay, so now in multiple linear regression model, this is kind of a final slide. So now as you know that in simple linear regression you have one dependent and one dependent variable. But when it comes to multiple linear regression, so in multiple linear regression, I mean typically it has something called dependent variable. So how we typically say dependent variable in different terms, they are the same terms. When someone say dependent variable, you can also say explained variable, a response variable. These are the same term, don't get confused with it. If someone say response variable, it is the same dependent variable. If they are saying you the explained variable, it means the same, they are talking about the dependent, the y. And intercept, and as it is multiple linear, it means x1 x2 x3 x, means there are many independent variable, and every independent variable will have some kind of a coefficient. Okay, so independent variable or independent variable is called explanatory variable or regressor. In some of the the research paper, you will see they're gonna write regressor or regression or something like that for y. Okay, and the y term, the u term, is error term, disturbance, and unobservables. It means your model is not able to observe those points. They are not able to capture the patterns. Error terms is obviously your model is not able to capture the term. That is why they are throwing in the error, right? So your multiple linear regression model, the equation looks like this. And just remember that response, regressor, explained, explanatory variables, these are the terms which are frequently used, so don't get confused. Okay, so just to give you a final clue that how your multiple linear regression typically looks like, and how you can create a image of multiple linear regression. Let's say a price of engine, right? Price of engine is to predict, you have to predict the price of engine. So let me go the left side, multiple linear regression. Okay, so this is your ML model, let's say, and this one is y is a price, and now you have a different independent variable. So let's say engine size, horsepower, peak RPM, length, width, and height of let's say a car, right? Maybe if you have a four-wheeler, right? So in that case, these are the some factors which play important role in the price of that model, right? So these are the few independent variables. So you have a six independent variable. So you have a six, you can say the explanatory variables. On the explained variable is a price. So price is being explained by the explanatory variable like engine size, horsepower to height, right? So now our model is giving the answers, I mean the different coefficients. So the equation is price equal to -8509, that is your intercept, plus the coefficient of a different, the explained variable, that is engine size to height. So once you run this model, and this model is going to give you some kind of a coefficient. So each and every independent variable will have some kind of a coefficients. So your model looks like this. Okay, so and when it comes to simple linear regression, obviously you will have one explained variable and one dependent variable. Okay, so explanatory and explained variable. Okay, so the price is minus this one, this is your intercept, and the coefficient will have only one independent, so you will get a coefficient of this. Okay, so this is how your simple linear regression model looks like, and multiple linear regression looks like. And you can easily interpret, for example, length is negative here, in this case length doesn't matter, so somehow it has a negative correlation somehow. And also you can capture r square value. Okay, so there are different way to come up with the model, the performance, that the model which you have created has a significant effect on dependent variable through the independent variable. Okay, this is the summary of your regression model. Okay, so you can also interpret, as I have already explained you, how you can interpret the R model. Okay, I mean the output of multiple linear regression, or maybe simple linear regression. This is the output of R. It's a similar, it's not like a different than the Python, but the way they are depicting. So I mean the best part is that they are also depicting this asterisk value. This is the significant. But if you see the length is negative, which is not significant, okay, 0.5. It means if you remove the length, your model gonna give you, I mean, it's a redundant, or you can say it's not useful. It doesn't have an effect on price of the model, right? Length. So you can remove it, okay, because it doesn't show any kind of a significance on the price of a model, right? So you can remove it, okay. So these all things I have interpreted it, okay. So I mean, before you go for uh, before I wrap it up. So Sakshi, are you there? Sakshi, are you
Yes,
there?
I'm here.
Okay. So I am giving one assignment. Just each one of you just look at it. Just let me stop presenting it and let me show you.
Okay, sir.
Just give me a minute. Let me just pull out the assignment. Okay. Just okay. So let me show you the assignment. Okay. If my screen starts showing, just let me just confirm it. Is it showing?
Yes, sir, it's visible.
Okay. So this is your assignment, and somehow it is uploaded in your Google Classroom, so it will show you. Okay. So this is your assignment. So I mean, there is one huge case. A research paper is also there. Okay. Just read that research paper, and I mean, the background of this is assignment is that someone has written the research paper and the huge case. So this is a top tier holiday, I know, the company, and they just want to, I mean, they just hiring you as a business analyst or data scientist, and you have been assigned this huge case, and you have to, do some kind of, the Python programming. Data set is there in the research paper, so that you can help the organizations to improve the customer experience and with the limited resources. Okay, so I mean, the first question is your, this regression analysis. You have to train the model. Data set is there in the research paper, and you just Python only. Okay, and what kind of a recommendation you will give to the this this organizations to improve the customer experience, and just try to formulate some kind of a strategy.
LLP.
Mhm. Yeah.
Sir, what is the LLP meaning?
LLP is limited liability, this
Okay, okay,
organizations.
sir. Okay, sir.
Okay, so this is just an organization. So, I mean, you have to come up with some kind of a strategy as well. I mean, I know you people might have studied this strategy subject. So, I'm just combining all three so that you'll have holistic view of answering it, because it's not just uh, give you the Python programming, also apply some kind of intelligence to it. Okay, because in real world, when it comes to corporate, you have to think through all the subjects which you have learned, and you can apply it. Okay, so this is 30 marks. Okay, and uh, don't just 5 is just 10 10. Okay, and then we'll convert it into 15. Okay, so this is 30 marks. Okay, and
Okay,
you have
sir.
to submit it by 2nd March. So I'm giving a week's time. Okay, so it is uploaded in Classroom. It will reflect you around 1:30 or maybe okay at 2. Okay, and
Okay, sir.
there is a no word limit, and just try running the code, and also you have to submit the code to me, and the screenshot of the code you have to apply it, and don't use chat gpt, don't use internet, and also add plagiarism report at the end. Okay, it should not be AI generated, results should not be AI generated. Okay, so okay, try to write in your own language, and try to give it a touch that it should be coming from your mind, not from the AI. Okay.
Okay.
So this is your assignment. Okay, try doing it by, because after that system will not take this assignment. So it is there. Okay. So 2nd March, a week's time, and try finishing it up. Okay. So this is all from my side. So Sakshi, if you are there, just take an attendance. Okay.
Yes, sir.
Yeah.
Okay.